Order in the court. The Supreme Court for Molecular Justice is now in session. Today we examine the case of thalidomide, R thalidomide and S thalidomide. How do you plead?
Not guilty, Your Honor. I'm R thalidomide and I just help with morning sickness and nausea. And I'm S thalidomide. I'm just his mirror image.
The evidence suggests otherwise. S thalidomide, you have caused some serious damage.
But what about my brother? We're the same. You cannot separate us. No!
This case changed how scientists test drugs. Now they look carefully at molecular structure because even the most tiny changes can have the most devastating consequences. Hello and welcome back to another episode of Solving for X. I'm Fatima, your left handed host for the day.
And I'm Nuha and I'm right handed.
Ought to mention handedness, right? But that is today's topic of interest.
Fatima, what would you think of if I asked you to name a tool that could break all of life and all of biology and turn medicine into poison? I'll give you a hint. You look at it almost every day.
A mirror?
A mirror. Well, of course, I am exaggerating a bit.
Before you confuse our listeners, let's dive into this. Put on your thinking gloves and
Thinking gloves? Wow, I know about thinking caps, but thinking gloves?
yeah, well, wearing gloves will allow you to feel the science we're about to explore. Try wearing your left hand gloves on your right hand and vice versa. It will fit, but it will definitely not feel right.
This is what chirality feels like. Though both your hands have the same arrangement of five fingers and look exactly the same, and in fact, if you placed a mirror in front of your right hand, it would appear as if the buddy in the mirror was putting up his left hand. But the right hand gloves don't seem right on the left hand, right? That is because they're not the same. And here enters the mastermind, stereochemistry.
Well, stereochemistry just means arrangement of atoms in 3D space. But a simple twist or swap can turn medicine to mayhem.
In a compound, especially the life forming carbon, if all four atoms or groups attached to it are different, then it is called a chiral carbon. This can show us the magic of stereochemistry.
Okay, imagine a carbon atom as the center of a small roundabout, like any of those traffic circles.
And four different cars are entering the roundabout from four different directions. Say a red car, a blue car, a yellow truck, and a green bike.
Since each vehicle is coming from a unique direction, the roundabout now has four distinct groups attached to it. This is our chiral carbon. It's a carbon atom bonded to four different things. Now here's the twist. Pun intended. You, you can arrange those cars going around the roundabout in one way, or you can flip the entire scene in a mirror and get a different arrangement. It might look the same at first glance, but it is definitely not the same. Chirality is known to play tricks like this. It even sounds like a Harry Potter spell. Chirality.
Chirality is such a trickster indeed. It gives you two versions of the same molecule called enantiomers. They're like twins with identical appearances but completely different personalities.
One looks like a cinnamon roll and is a cinnamon roll, while the other still looks like a cinnamon roll but could kill you. And you can't just rotate one to match the other. No matter how much you twist or flip it, it never lines up with its mirror image. Just like your left hand never quite fits into the right hand glove.
Chirality even comes from the Greek word "keria," which means hands. Sorry, the Greek nerd in me couldn't hold it in any longer.
Of course. So much about hands for a single episode.
Well, you might want to hold on to those hands. because life as we know it is literally built around them.
Wait, are you saying molecules have a hand preference? Like like amino acids are left-handed like me or something?
Bingo! Nearly all the amino acids, except for glycine, exist in mirror image forms, like right handed and left handed gloves. These gloves are called as L and D enantiomers. Although the two enantiomers exhibit identical physical and chemical properties, living organisms only use amino acids of L chirality. We call this homochirality.
If amino acids and proteins are left-handed, then what about DNA? I thought Watson and Crick model was a right-handed helix.
In DNA, the deoxyribose sugar is right handed. These are known as D sugars. I guess nature just picked a side and stuck with it.
But these sides of chirality are extremely important in our body. Without it, proteins couldn't fold into the stable 3D structures,
Which are important for their function.
and the double helix structure in DNA would also not form.
It's like trying to build IKEA furniture with the instructions in Klingon. Kashtak nukje.
That does sound like a nightmare.
Chirality is also important in the interaction of molecules with receptors. The receptors behave differently in binding to the stimulant molecules. That is, they are enantioselective.
So, enzymes and receptors bind to only those molecules with the correct 3D structures and chirality. If the wrong enantiomer
Or twin.
binds, it may block the reaction or even cause errors, like a wrong key in a lock.
How exactly do these small changes drastically change a molecule's function?
Well, it's all about fitting.
Like trying to fit into a dress after a birthday meal.
That small difference means they fit differently into enzymes or receptors, which are also super shape specific. This can also affect physiological reactions such as smell and taste.
Like carbone, which is a terpenoid found in essential oils. It smells like mint in its L form, and caraway, cumin, in its R form. Limonene tastes like citrus when right handed, and pine when left handed.
These differences can also be harmful, like in the thalidomide case that we saw at the beginning. Thalidomide was developed in Germany in the 1950s and it was used as a sedative. The animal testing results seem to show that even very high doses were not harmful. In human patients, it seemed that the new medicines had remarkably few side effects.
It was prescribed as totally safe. It was used in treatments for flu and also the morning sickness and insomnia associated with pregnancy, despite the fact that no safety testing had been done on pregnant animals.
People also argue that in the 1950s, no new medicines were tested in pregnant animals because scientists did not yet understand that the fetus could be damaged by external factors.
Nevertheless, by the late 1950s, babies were starting to be born with missing or shortened limbs. In June 1961, an Australian doctor, William McBride, succeeded in getting the Women's Hospital in Sydney to stop prescribing thalidomide to pregnant women after he and midwife Sister Pat Sparrow saw several cases of birth defects and connected them to the drug.
When animal tests did finally happen, they showed a range of effects that thalidomide could have caused, from miscarriage and reabsorption of the fetus in the womb to damage to the eyes, the heart, the brain, and the distinctive limb malformations depending on the stage of pregnancy.
Let's look at this from a chemist's perspective. The tragedy occurred because thalidomide was sold as a racemic mixture, which is a 50-50 blend of both enantiomers.
The R enantiomer has the desired sedative and antiemetic effects. An antiemetic is a medication or treatment that is used to prevent or reduce nausea and vomiting.
But the S enantiomer is teratogenic, meaning it can cause severe birth defects by interfering with fetal limb development.
Even more critically, in the human body, the R and S enantiomers can interconvert. making it impossible to administer only the same safe form. This led to over 10,000 children worldwide being born with limb malformations.
The thalidomide disaster led to much stricter drug regulations worldwide. Now, pharmaceutical companies have to carefully evaluate the stereochemistry of their drugs during development, testing, and approval.
Chirality isn't just a life or death matter in medicine, it's also opening incredible possibilities in fields you might not expect, like nanotechnology and optics.
Turns out, nature's handedness has inspired scientists to create materials that can manipulate light in mind bending ways.
Imagine nanostructures so tiny and precise that their chirality can twist light itself, or it can filter out only specific polarizations of light. Chiral molecules have the ability to rotate plane polarized light to dextrorotatory, which is clockwise, or anti-clockwise, that is lever rotatory. Imagine shaking a rope back and forth. That is how plane polarized light travels. Unlike normal light, which is like shaking three such ropes in perpendicular planes.
So many ropes. And this optical magic can be used in detecting the correct enantiomer, which is critical for pharmaceutical quality control and food testing.
And this chirality spell does not even stop here. Chiral molecules can even filter electrons based on their spin. This is the chiral induced spin selectivity. Try saying that 5 times in a row.
Chiral induced spin selectivity, chiral induced spin
No, no,
selectivity.
no. I mean the listeners. Spin filtering could lead to better spintronics. These are electronics that use the spin of electrons rather than their charge. That means faster and more energy efficient computers.
That's just scratching the surface. Some researchers are even exploring how CISS might play a role in biology, like how electron transfer in our cells might prefer certain spin directions because of the chirality in biomolecules like DNA.
In fact, polarization is used in holography and high contrast imaging. Instruments that measure circular dichroism. These are basically devices that measure how differently light is twisted by chiral molecules. These are being proposed for space missions, and the purpose? Detecting life outside our world.
Cool.
Yeah. It is suspected that if life exists beyond Earth, it would also exhibit chirality, just as our amino acids do. Do you know about the Murchison meteorite?
Murky what?
Murchison. It's a meteorite which fell in Australia in 1969. Over 70 different amino acids, including several that are chiral, have been found in it. And guess what? An excess of left handed amino acids had been discovered, suggesting that some process in space favored the formation of one chirality over the other.
Oh god, this is just like that theory of spores, panspermia, which we talked about in the evolution episode. Imagine one of the most compelling pieces of evidence for the presence of chiral molecules in space comes from the analysis of meteorites. Literally, alien chemistry.
Even studies of the dense regions of gas and dust, where stars and planets are formed, have revealed the presence of chiral molecules.
Astrochemist McGuire and his team have reported in Science the discovery of a chiral molecule in interstellar space. The compound, propylene oxide, was found in Sagittarius B2, a cloud of gas and dust near the center of the Milky Way. This discovery suggests that chiral molecules have existed long before solar systems.
If these molecules were predominantly right handed, they might have influenced the formation of other right handed molecules, including DNA, well, before the formation of our sun.
Whoa, 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 let's not get too ahead of ourselves. Some biochemists who study chiral molecules in meteorites caution that linking these observations directly to DNA chirality is challenging. The processes that occur between molecular clouds and the emergence of life remain unclear. We don't even know if propylene oxide is right or left handed.
Yes, yes. But what about the hypothesis that involves the influence of circularly polarized light? Lab experiments have demonstrated that circularly polarized lights can break bonds in chiral molecules more efficiently on one side. This leads to an imbalance in chirality.
Light breaking bonds? Sounds like something Apollo would do when he's mad. Ha, another hyacinthus.
Yeah, okay. If you're done obsessing.
Yeah, yeah.
So, another theory suggests that weak nuclear forces, which are inherently chiral, could influence the formation of chiral molecules during the early stages of chemical evolution.
Then there's the serene hypothesis. R. Graham Cooks, distinguished professor of analytical chemistry in Purdue School of Science, believes that serene was the first biological molecule to make a chiral choice, possibly one of the root steps in chemical evolution itself. Proteins followed the lead taken by serene, and that's how we ended up with the twins we know today.
Remind you, there has been no agreement about how it all happened. This problem has even deepened because of a NASA funded discovery that RNA can favor making the building blocks of proteins in either the left hand or the right hand orientation.
In an experiment, the researchers simulated what could have been early Earth conditions of the RNA world. They incubated a solution containing ribozymes and amino acid precursors to see the relative percentages of right handed and left handed amino acid phenylalanine that it would help produce. They tested 15 different ribozyme combinations and found that ribozymes can favor either left handed or right handed amino acids. Irene Chen of the University of California, Los Angeles, said that the experiment demonstrated that ribozymes can favor either left or right handed amino acids, indicating that early RNA worlds didn't always prefer the same type of amino acids we see in living things today. In any case, understanding the chemical properties of life can help us figure out not just how life works on Earth, but maybe even how it could begin elsewhere in the universe, says Jason Dworkin, astrobiologist at NASA.
It's remarkable how something so seemingly simple, like left and right, unfolds the layers of mystery, meaning, and cosmic significance the deeper we look. It's as if the universe rewards our curiosity with purpose.
Yes, glorious purpose. And the future holds that for chirality. With so many applications emerging, ranging from plasmonic metamaterials and
Wait, metamaterials are materials engineered to exhibit properties that are not found in naturally occurring substances, like negative refraction or artificial magnetism. But what's pulso? Pulso what?
plasmonic. Yeah.
Oh, yeah, yeah, same thing. Yeah.
Well, that refers to plasmons, which are, in a way, the collective oscillation of free electrons in a metal when they interact with light. And plasmonic metamaterials use nanostructured metals like silver and gold to bring out the plasmonic effects, like gaining some extra control over what you can do with light. Maybe even seeing details beyond the wavelength of light. Or with bending light, we can mimic invisibility in objects.
So, at least theoretically, invisibility cloaks and Doraemon's big light can exist. Wow.
And in the near future, it might not just be theoretical.
Quite recently, researchers at the Fritz Haber Institute have achieved a significant milestone by attaining a near complete separation of quantum states and chiral molecules. This breakthrough paves the way for exploring fundamental physics, such as the understanding of universe's asymmetries.
Like we mentioned earlier, even biomedical industries are booming with new ideas, with advancements in precise biosensing, antibacterial therapies, cancer immunotherapy, tissue regeneration, and the overall effectiveness of targeted medicines. And in all of this, chirality has a big hand.
Pun intended, I hope.
Haha. And even the discovery of chiral molecules in meteorites, like the Murchison meteorite, suggest the universal nature of chirality. And maybe this would be the pathway to us finding footprints of life elsewhere.
How fascinating all of it is. From fundamental physics to cutting edge medical applications, chirality continues to be a pivotal concept, driving innovation and discovery.
In the twist of a molecule lies the twist of fate itself. Chirality is not just a feature of life, it is the fingerprint of the cosmos.
And that's a wrap. Today, we looked at stereochemistry and chirality, how tiny differences in molecular handedness makes a huge difference in biology and how they work in our body. The thalidomide tragedy taught us the importance of testing and the dangers of chirality.
Modern nanotechnology and optic tools lighten the mood to show us how we can actually see and change these differences. It's amazing how technology is shaping the future of medicine and research.
So, on this optically amusing and optimistic note, we thank you for tuning in to this episode of Solving for X.
We'll be back next week with some artistic license and a whole lot of curiosity. Only on Spotify and YouTube.
I'm Fatima,
And I'm Nuha.
diffusing out.